Hello, everyone. This is Nick Payton from SigOpt. We're going to go ahead and get started. Thank you all for joining us today for another in our webinar series. Last week, Patrick Hayes, our CTO here at SigOpt, presented on some pretty compelling insights for techniques and tactics for deep learning optimization at the ODSC conference that happened in South San Francisco. And given some of the response that we saw at the event, as well as just general interest in deep learning and how to optimize deep learning models, we thought that it would be valuable to share some of these insights more broadly, which led us to schedule this webinar right after the conference itself. So today, I'm joined here by Patrick Hayes, our CTO, and he's going to both share a little bit more about our product and how it works, just to give everyone a sense of what SigOpt does, and then go a little bit deeper into some pretty interesting techniques, some interesting research on deep learning optimization, as well as a little bit of research around the cluster management challenge within the deep learning optimization framework itself. So during this webinar, we are going to be answering questions. Use the GoToWebinar question asking part of the control panel, and I'll be triaging and making sure that we get to all of them throughout the webinar. In some cases, we'll stop and answer them directly if it's core to the subject area that we're discussing at that point in time. Otherwise, we'll hold some time for the end to answer the rest of them. And without further ado, we'll dive right in.
Thanks, Nick. All right, hey everyone, my name is Patrick. I'm the co-founder and CTO at SigOpt. I'm going to be talking about methods for optimizing your deep learning models. I'm excited for this conversation because this topic is of particular interest to me. So we're going to discuss this optimizing deep learning models in two particular contexts. First, in the context of deep learning models that are particularly expensive to train. And second, in the context of a relatively resource-constrained team that has limited access to DevOps. So we'll jump right in. So for those of you who haven't heard of us, we're a relatively young company with a relatively bold mission. Our mission is to build software solutions that empower modeling experts. In our experience, having access to the right solutions can make the difference between experiment success and experiment failure. And our hope is to make it much more likely that you are successful. So what does this actually mean? Let's take a broader perspective. So at SigOpt, we see that there are at least three critical components to any successful model development process. First and most importantly, there's the domain expertise, the insight that you, as the modeling expert, bring to solving your tough problems. This, of course, should always be handled directly by the experts and never outsourced. Our goal is to give those experts the chance to spend the majority of their time working in this space, iterating on their objective metric and how it connects to their business outcome. Secondly, there's a certain amount of proprietary infrastructure required to ingest, clean, transform, analyze your data and manage the model lifecycle from development to production. This is typically handled by your DevOps team or some other internal infrastructure team. There may be software solutions that assist here, but a lot of this work has to be custom because the problem is relatively proprietary. And third, there's the subset of repeatable tasks that are the same for every single model development and production process. And these are the tasks that should be automated with software, but they're also the tasks that should typically be handled by third-party software because they're the same for every model and therefore can benefit from SaaS scale. And so these are the solutions that SigOpt develops for our customers. And just to briefly go over my background and journey to founding SigOpt, I studied math and computer science at the University of Waterloo. Then I worked in industry at companies like Facebook and Foursquare, developing products to scale to millions of users. Scott, my co-founder Scott, and I founded the company about 4 years ago in 2014, where we were funded by great investors like Y Combinator and Andreessen Horowitz. And now today as CTO, I'm responsible for building scalable solutions for our customers and the technical challenges of optimizing models at scale. So at SigOpt, what we provide is a hosted solution for hyperparameter optimization. If you're not familiar with this term, hyperparameter optimization is a technique for finding the best version of your model. Finding the right hyperparameters can be the difference between a model that performs poorly and a model that can dramatically impact your business. Some of you may have heard this by other names, like hyperparameter search or model tuning, and it can also be referred to by the specific method used. There are naive methods like grid search or random search, and there are more sophisticated techniques like Bayesian optimization. SigOpt provides a SaaS solution that hosts the most cutting-edge hyperparameter optimization techniques for modelers. How does it work? We provide a black box optimization software as a service solution. In short, that means that we tune your models without ever touching your underlying models or the training data. Your modeling experts will use a few lines of code to install our library and call our API. Then we will automatically suggest new hyperparameters for you to try, and you report back to us how well they did on the metrics you care about. As you repeat this process, we learn about your model and find the parameters that will make your model the best it can be. This automates this expensive task, so your experts can spend that time on innovation instead, resulting in an accelerated model development process. And in fact, we find that most teams will actually transform this process from a sequential step-by-step model development into a more iterative, innovative prototyping process. So just to highlight 3 things about this. First of all, we never access your training data or your model code because we know that's proprietary and secure. So this, we want to ensure our customer security, safety, and privacy. The box on the left that's highlighted here is your system, which we do not access. And this allows us also to work with any type of model, any programming language, any framework, or any infrastructure. We also run an iterative automated optimization process to accelerate experimentation. Because it's completely automated, this takes the task off your experts' plates. And finally, we are specifically built to scale for the enterprise. Our robust API, sophisticated optimization solution, and comprehensive web dashboard are all built with enterprise-grade reliability as a first priority. So here's how it works from the developer's standpoint. We've designed it to be easy to use so the user doesn't have to implement complicated optimization techniques themselves. First, you install the client library and instantiate it with your API token. The example here is written in Python, but as I mentioned before, we support any programming language, model, data, or library. Secondly, your developers will create the experiment, defining the parameters that they want to optimize. We support any parameter type, like continuous parameters, which are real numbers, integer parameters, such as 1, 2, 3, 4, etc., or categorical parameters, where you're choosing from a list of predefined values. Also highlighted here, we allow you to parallelize the training of your models, so you can train different versions at the same time. We support up to 100x parallelism. And you can define a budget to limit the amount of compute you want to use to solve this problem. The next step is that you parameterize your model. This is intended to be a slight modification of your existing model code, where you allow SigOpt to suggest values for the parameters you're tuning. Our goal is to make this as small a modification as possible from the code you're already writing, to make integration as easy as possible. Your team will also define the objective metric that you'll be optimizing, which in this example is the accuracy of the classifier. Then finally, you include a few lines of code to trigger the optimization loop. This is a repeated process where you request suggestions from SigOpt, evaluate them, and then report back how well they did. This results in a fully optimized model in just a few lines of code. Throughout this whole process, you have access to an easy-to-use web dashboard that provides you and your team with a simple way to track, manage, and reproduce experiments. It includes a full history of everything you've run so far, as well as in-depth insights on any individual experiment. We include organizational control so that you can set permissions for who on your team is able to see this and share results within the rest of the team. There are a lot of benefits here, but I want to call out a few. The first is it optimizes your models much more efficiently than other methods, which ensures the maximum utilization of your compute capacity. Secondly, it accelerates this tuning process, so your experts can spend less time building tuning and more time building additional models. And third, it improves the accuracy of each model that it optimizes. While there's no free lunch here, we are unlikely to outperform a custom solution built for a specific model, but on average, we outperform other methods when applied to a wide variety of models. And I've included links here for you to explore some of these results in further details. At SigOpt, we spend a lot of time benchmarking and measuring our impact to make sure our claims here are as rigorous as possible. I've shown you a relatively simple step-by-step process here, but it's important to note that we also have many advanced features that we didn't show. In fact, our solution is the most complete and advanced optimization solution available. We spent years building advanced features in which are built for our customers' specific needs. And we're still the only provider of many of these features today. The features highlighted in red are the ones that only we provide in the market. So I've described our standard solution, but for the rest of this talk, I want to focus on some additional advanced techniques and problems that we've encountered and how to solve them. So it's important to reiterate that at SigOpt, we focus on solving problems for applied AI. That is, our research and product are specifically designed to solve real-world enterprise challenges. We're not interested in going after academic benchmarks or attacking problems that aren't found in the real world. But applied AI introduces these unique challenges. And these unique challenges are where my team spends the majority of their time. And here are a few of those examples. I won't go over each of these because they're all covered extensively on our blog, which features in-depth discussions of our topics of research. But today I'm going to focus on these last two. Training models, which have very lengthy training cycles, and cluster orchestration to make effective use of your compute that's available. And specifically, we're going to consider these two challenges in the context of deep learning models that are particularly expensive to train. For our customers, these expensive models will often go untuned because the standard methods could take days or weeks, which is often prohibitive for the team. This isn't just an academic exercise. We're seeing an explosion in the amount of computation required for sophisticated modeling. Here's a chart from a recent OpenAI blog post. And in short, from AlexNet in 2012 to AlphaGo 0 in 2017, there was a 300,000x increase in the compute required to train these sophisticated models. But we've seen this before. As early as the 1800s, when coal burning technology became more efficient, you might have expected the amount of coal consumed to decrease. But the opposite happened. The amount of coal burned each year actually increased. That's because coal became a cost-efficient fuel source, so the demand increased dramatically more than the savings of the increased efficiency. Some of you may know this as the Jevons paradox. So the problem of lengthy training cycles is unlikely to be solved by hardware innovation alone. As GPUs get faster, more sophisticated models will fill the void, and our most sophisticated models will still take a long time to train. And more broadly, these types of expensive models are becoming more ubiquitous. Deep learning models are being used to tackle speech recognition, deep reinforcement learning, and computer vision. Each of these domains involves complex models as well as huge data sets. And because the long training time required to train even one instance of these models, hyperparameter tuning with the standard techniques is often difficult or impossible. So to put these long training times in context, we'll consider a case study. With TPUs, you can train ResNet 50 on ImageNet in about 12 hours. The actual model and timing aren't so important here, but this is reflective of the time that many real use cases take. So to optimize 12 parameters on this model with standard methods, you should train at least 120 distinct models in order to find a good version. So in total, you're looking at about 60 days of total compute time to get to an optimized version of this model. And the question here is, can we do better than that? So this is the first of the two challenges that I'll address today to help solve this problem. How can you improve training and tuning efficiency to optimize these particularly expensive models? Now, this is an area of very active research, but I'm going to focus on one method that we have found particularly useful for solving this challenge, and that's multitask optimization. Multitask optimization starts with a simple idea. If we can learn from partially trained models and apply those insights to the fully trained model, then we can collect information about our model at a reduced cost. In this sense, when optimizing, we have multiple tasks that are available where some of those tasks are cheaper than others. By training with the cheaper tasks, we can learn about how our model performs without having to wait for it to completely finish training. This allows us to tune a model much more efficiently than would otherwise be possible. The idea relies on relatively recent, but also relatively compelling research. Swirsky, Snowick, and Adams wrote a foundational paper that introduces the concept and tests it with results that point to success. Conceptually, multitask blends two techniques that some of you may already be familiar with. On the one hand, it relies on the previously mentioned idea of sampling partial cost versions of the model, and on the other, it relies on Bayesian optimization to efficiently explore and exploit the search space. The goal is that this approach will introduce additional efficiencies and accelerate the training process. But once again, this may work well in theory, but in the world of applied AI, multitask optimization comes with unique challenges. In particular, the cheaper approximations of a model introduce additional noise and bias that makes them more challenging to practically apply to these problems. So while the technique is powerful, we have to be careful to use it in settings where the cheaper tasks will actually inform us about the full cost problem. Otherwise, we risk lengthening the tuning process since the cheap tasks will not be good representations of the full cost task. We've found in practice that two methods that work very well to reduce this bias are by defining your cheaper tasks in one of the two following ways. The first is to train your model on a reduced subsample of the training data. And the second is for deep learning models to train them for fewer training epochs. Here's an example that works well from the University of Freiburg. Here's an example from the University of Freiburg where they trained an SVM model 400 times on the MNIST dataset. These charts show how the performance of the model responds to changes in the regularization parameter C and the kernel parameter gamma. Now, going from left to right, you have a 1/128th sample of the data, a 1/16th sample of the data, a 1/4 sample, and the full data set. What's important here is that you can see that these surfaces have roughly the same shape, which tells us that the information learned about the cheapest model can, in some capacity, be transferred to the more expensive problem. That means that you can learn about the full cost task more cheaply by sampling observations from the partially trained model. And this is exactly the type of problem where multitask optimization can perform well. Let's dive one level deeper. Here we have two functions, a blue function and a green function. And our goal here is to learn about the blue function. We can also plot below this the information gain. The blue line is the information gained by sampling from the blue function, and the green dotted line is the information gained by sampling from the green function. Since our goal is to learn about the blue function, the information gained by sampling from green is low. And this makes sense because we're sampling from the wrong function. Now in the middle chart, you see what happens if these two functions are correlated. In this case, sampling from the green function does tell us quite a bit about the function in question. And you can see that by a elevation in the green information gain line. However, it's never going to be as good as sampling from the function itself. So what's the point? Well, what if the green function were cheaper to sample from, and if furthermore, we scale the information gain by the cost of sampling from the function? Then we could actually be collecting information more efficiently, and the rate of information gain could be higher from the green function. And that's what we see here. This shows the power of multitask optimization, where if it's done well, it can be an inexpensive way to learn a lot about expensive functions. This is an area of active research with lots of great minds working on solutions for this. Another you may have heard of is early termination, which is also occasionally called hyperband after a specific implementation. The premise of early termination is to terminate the training process early if we predict that it will not eventually yield good results. Both methods use the premise that information from partially trained models can inform our beliefs about the fully trained version at a reduced cost. The University of Freiburg again published some research comparing these methods. They present a task-based algorithm, Fabolas, which has successively smaller tasks for fractions of the data set, as well as a simple multitask reference implementation, which has one cheap task and one full cost task. They also compared a hyperband and then basic Bayesian optimization techniques as a baseline. The comparison is done on an SVM model trained on several different data sets, which you can see here. And here are the results. For these tasks, the goal is to minimize the test error. And so for our purposes, we're interested in seeing how quickly these methods can arrive at an optimal configuration. So that is, the faster that the line approaches the y-axis, the better performing it is for expensive models with lengthy training cycles. The green line is the paper's task-based Fabolas implementation, and the blue line is the simple multitask implementation. In every case, the task-based methods outperform the standard methods and hyperband, which is represented in orange. Now let's go from the research to the real world. How, as a developer, would you implement this strategy? We've made it very easy. As we discussed at the beginning of the talk, our goal is to build software solutions designed to empower experts. In general, practitioners can use SigOpt for hyperparameter optimization with just a few lines of code, as shown here. And with just a few additional lines, as highlighted with the blue box, any user can define the tasks to run a multitask optimization experiment. As you can see here, we've constructed an example where our tasks are defined by the number of training epochs. So we have cheaper tasks which train this deep learning model for fewer epochs. Then, during hyperparameter optimization, the experiment will trade off exploring the problem with the cheaper tasks and exploiting that information to find solutions in the full cost task. Once you run the experiment, you can look up its performance on the web. These are screenshots from our product, but note that we're not sharing any data from customer experiments because those are proprietary. Rather, these are internal experiments we've run to test this method on real-world models. This plot shows the accuracy of the partial cost tasks in gray versus the full cost experiments in blue. As you can see, there are many more partial cost tasks, and they vary wildly in performance, but they've guided us to this cluster of high-performing blue full cost tasks at a reduced cost. You can also see how your model is improving over time. At the beginning of the experiment, you can see how the gray partial cost tasks quickly reach a test accuracy of about 0.72 in less than 20 trials. Then we start to include the blue full cost observations, which start to refine that value and get to an even better value as the experiment continues. You can also see the distribution of your tasks across costs. You can see that the cheapest task on the right has the most samples, and this is what we typically see because the cheapest task presents an opportunity to learn about the space inexpensively. The full cost task on the left are sampled less frequently because they're the most expensive, but since this is the task that the developer will typically productionize, it also is sampled to collect the best solutions. This experiment also features a medium cost task, which is seen in the middle, which is also sampled. The research the University of Freiburg did was a great inspiration for us, but we wanted to use this opportunity to benchmark performance in an applied setting. Recall that for multitask optimization, the goal is not strictly to find the optima. Instead, it is whether or not you can find a high-performing model in relatively few iterations. In this case, we tested a convolutional neural net, which had 10 hyperparameters, and we set the budget at the time it would take to train 25 full-cost models. And we ran across a variety of techniques, including random search, early termination, and multitask optimization. In this case, we observed that random search and hyperband performed similarly, and multitask optimization significantly outperformed both. And these improvements were consistent across multiple dimensions. For hyperband, we ran with different numbers of rounds of successive halving, and for multitask, we ran with different numbers of tasks. And in both cases, we evaluated with different degrees of parallelism, which is the number of models being trained at the same time. This represented an average improvement of about 7 percentage points. And this is a notable difference. In fact, it can be the difference between whether a deep learning model does or does not make it into production. Now that we've explored techniques for making tuning and training more efficient, let's turn to a new problem. How can teams with relatively few resources manage clusters efficiently for these complex models? In many cases, cluster management and efficient parallelization can generate high-quality models in much less wall clock time. Now, this is not always a challenge. In some cases, you can train a model on your laptop, and the DevOps challenge does not exist. But for a lot of our customers, this isn't the case. In fact, there are often multiple levels of complexity. The team could have multiple users sharing resources. Each of those users might be conducting multiple experiments in parallel. Each of those experiments may need to be trained to train multiple models in parallel. And each of those models might need to be trained on multiple GPUs in parallel. As you can see, these levels of complexity all compound with each other and present a unique challenge for teams that are creating models at scale. When this complexity is introduced, multiple problems tend to pop up, including challenges related to managing infrastructure, scheduling, dependencies, logging, and more. So we've abstracted all of this away for our users in a command line tool to manage these challenges. And we call this tool SigOpt Orchestrate. To enable this, Orchestrate containerizes your models with Docker and uses Kubernetes to execute them in parallel across your cluster. This has many advantages, but the most notable is that it provides a stable, scalable way to submit training jobs to your cluster of available machines and have them scheduled and executed in parallel. So SigOpt Orchestrate makes this simple. First, you use our command line to launch a cluster of machines on your favorite cloud that you or your team will use to run your experiments. Then you schedule optimization experiments to get distributed to your cluster. This will run the containerized version of your model on multiple machines. Next, this automatically integrates with our tuning API to conduct hyperparameter optimization. And finally, you can monitor these experiments on the web as they progress, including the underlying infrastructure and more. The goal is to fully abstract the infrastructure away from the developer so they can focus on their expertise, which is modeling. So we want to make it as fast and simple as possible to integrate Orchestrate into your model. So I'll show you how it integrates now. This file should look pretty familiar. It's a pretty standard random forest classifier. You take your standard model code and with as few modifications as possible, we want to make it really easy to integrate with Orchestrate. So first, you replace the parameters you want to tune with calls to this Orchestrate Python library, which you can see highlighted in the first box. Those values will be replaced based on the hyperparameter suggestions. Then you evaluate your model and report the metric you want to optimize, which is seen highlighted in the second box. This is intended to be as frictionless as possible and require the fewest changes to your existing code. Next, you'll define a model configuration file. This allows you to define setup code or dependencies. And here's also where you define the hyperparameters to tune. And you can also specify the number of models that will be evaluated in parallel and how many training runs you want to execute. You can run multiple experiments on the same cluster. The SigOpt run command containerizes the model and sends it to the cluster to be optimized. All the dependencies and setup are included and packaged. And then the experiment has begun. You can close your laptop and walk away. It's been scheduled to execute on your cluster at this point. You can monitor the status of your experiments through the CLI. You can see how far they've progressed and if there have been any failures, which you can see here with this experiment, which is progressing nicely with no failures. And it's easy to see the logs of all your models as they train. You can use this to monitor the progress of an in-flight training run to watch for errors or track progress. And finally, all of these results are available on the web. You can use this page to find the best results seen so far or to monitor the experiment improvement. So now we've covered both these problems. If you implement multitask optimization and automated cluster management, you're solving two of the biggest challenges for deep learning optimization. This will set up your team to optimize expensive models that previously may have taken too long to tune. And by optimizing more of your deep learning models, you're increasing the likelihood that they achieve a level of accuracy required for them to make it into production. Now let's revisit that original ImageNet example we discussed at the outset. With multitask optimization, you may be able to reduce the number of hours required to train the model from 12 hours to 4 hours on average using the partial approach to evaluation. This now translates to 20 days of training time instead of 60 for a full optimization run. But using a tool like SigOpt Orchestrate, it makes it easy to run it in 10x parallelism, which now gets you down to 2 days wall clock time from the original 60. This is how you translate advanced optimization techniques into real business value for your modeling process. If you're interested in more detail on this or any other optimization topic, please check out our blog. Our engineers provide detailed insights on their experiments and ongoing investigations into new optimization techniques. And thanks for your time. Whether you're a researcher, an enterprise, or an aspiring student, we have a version of our product designed for you. If you're interested in trying SigOpt Orchestrate, please contact us and we're happy to get you set up. Similarly for multitask optimization. I appreciate your attention today, and I'm here to answer any other questions.
Thank you, Patrick. And thanks for everyone who joined us as well today. One thing that I will mention, just to reemphasize Patrick's point, we are actively working with users on each of these products. So if you have a use case, we'd love to work with you on those problems as well. There were a couple questions that came through during the conversation. The first is asking how successful these products are when implementing these solutions. Just to give a sense of that, whatever we're able to share.
Yeah, of course. So a lot of our customers, of course, are we don't want to share anything proprietary from any of our individual customers. But what we typically find is that our customers gain a lot of benefits on a lot of different axes. So first of all, if they have models they care about, SigOpt will make those perform better. So if these models are driving value for their bottom line, we can increase that value and drive dramatic impact for these businesses. On the next level is improving the development process for these modelers. So previously, a lot of modelers we worked with would spend a lot of their manual time on these types of optimization, which is just simply not a great use of their time that these experts could be spending. It would be better for them and their business if they focused on designing new algorithms, focusing on their data set, new features, etc. So by integrating SigOpt, these modelers were able to go back to what they were great at and thus give them more space to innovate and develop higher quality models. So those are typically the two dimensions that our customers see a lot of success with.
Thanks, Patrick. Another question that we got. What if there are several objectives in the optimization? For example, if you have to compare and compete accuracy with AUC, could you use software to deal with that?
Yeah, absolutely. That's a great question. It is something we do support, and I'll go back to the slide where we kind of glossed over it a little bit, but we do support multi-metric optimization. That's when you have these competing objectives that you're trying to trade off. It does modify the problem slightly in that you're no longer searching for one single solution, but more trying to understand the trade-off between these two metrics that you're trying to evaluate. So you can imagine accuracy and AUC, or perhaps accuracy and prediction time. Finding, you can use SigOpt to kind of simultaneously optimize these objectives, and then at the conclusion of the experiment, have an array of different solutions that make different points along that trade-off spectrum.
Thank you, Patrick. And that's another, so along with visiting the blog to explore that, we have given presentations in the past on competing objectives and how to solve those. So if you navigate to our YouTube page as well, you can see a talk that Scott, our CEO, gave at NVIDIA GTC as recently as earlier this year in March. Another question we got is, could you talk about enterprise pricing? Just at a high level is fine, fixed and variable fees, etc. So I will take that, being the marketer here. Just at a high level, we are a SaaS product. As Patrick mentioned, we're a hosted solution for optimization, and it's easy to kind of implement us with a simple API-enabled approach. And so we do have your standard approach from a SaaS pricing perspective. Typically, what ends up happening is we don't have like a variation between fixed and variable fees per se. Instead, we approach this from the perspective of charging based roughly on the total amount of experimentation that you expect to do on our platform. So we do scale with the overall experiment. The price does scale with the overall level of experimentation. But we do try to structure our pricing so that there are pretty significant variable discounts as you scale up your total volume of experimentation as well. So we do charge as experiments go up, but we charge a lower incremental amount per, essentially each additional experiment you put on our platform. Happy to talk in greater detail about this. So feel free to reach out, to me directly, and I can connect you with the right salesperson on our team. My email address is nick@sigopt.com. But interesting question, going more in the business direction on that front. I'm personally happy to see those types of questions come through. And then just a general PSA announcement, because we've gotten a couple questions about the webinar and whether it will be recorded. This is being recorded, so I will be sharing this out to everyone who attended, and we'll be posting it on our YouTube channel as well. So you will be able to access this content going forward. And if you have any additional questions on this, on our techniques especially, or on how our solution could be utilized by your organization, we are happy to answer those questions. It looks like those are all the questions that we've received for now, but I appreciate everyone's time and attention, and thank you for joining us for this talk. And thank you, Patrick.
Thank you, everybody.